Welcome back to Python DSA. Today we're covering trees completely. We'll start from what a tree even is, build up through binary trees, BSTs, traversals, deletion, balancing, heaps, tries, and segment trees. By the end you'll have the full mental model and the Python code to back it up. Let's go. Ext. A tree is a hierarchical, nonlinear data structure, a collection of nodes connected by edges with absolutely no cycles. Click. The first thing to anchor is the contrast with the linear structures we've covered so far. An array, a linked list, a stack, a queue, all of them have one path from start to end. You go forward, maybe backward, but it's a single line. A tree has one root at the top, and then branches. Multiple paths, multiple directions, no way to loop back. The second key rule: no cycles. There is exactly one path between any two nodes in a tree. The moment you add a back edge and create a cycle, it stops being a tree and becomes a graph. The distinction matters a lot. Click. Real-world trees are everywhere. The file system on your computer is a tree. Your home folder has subdirectories, which have subdirectories, branching all the way down to individual files. HTML in the browser is a tree, the DOM. Organizational charts. Decision trees, in machine learning. In compiler abstract syntax trees, which is how Python itself understands your code. Click. The diagram makes the structure concrete. Node A is the root. It has no parent, it's at the top. From A the tree branches to B and C. B branches further to D and E. D has children H and I. The green bordered nodes, H, I, J, F, G, are leaves. They have no children. Every node except the root has exactly one parent. Before we write a single line of code, we need a shared vocabulary. The diagram on the left labels everything. Root, the single top node with no parent. In the diagram, node A, at depth 0. Node, any element in the tree. It holds data and references to its children. Edge, the connection between a parent and a child node. Leaf, a node with no children. E, F, and G in the diagram are leaves. Parent and child. Every node except the root has exactly one parent. A node's immediate connections downward are its children. Siblings, nodes that share the same parent. Click. Depth, the distance from the root to a given node, measured in edges. The root is at depth 0. Its children are at depth 1. Height, the length of the longest downward path from a node to a leaf. A leaf has height 0. The height of the whole tree is the height of the root. Subtree, any node together with all of its descendants forms a valid subtree. Degree, the number of children a node has. Click. For the tree on the left, height is 3. The longest path goes from A down through B, D to G. Total nodes, 7. Leaves, 3. These terms will come up constantly in the next 20 slides. Make sure they click now. Ext. Not all trees are the same. Let's define the 4 main structural variants of binary trees. Each has specific properties and specific use cases. Click. Binary tree, the broadest category. Each node has at most 2 children, called left and right. There are no other constraints. A single node is a valid binary tree. So is a linked list that only uses left pointers. The shape is completely unrestricted. Click. Full binary tree, a stricter form. Every node has either 0 or 2 children, never exactly 1. No node is a half-filled branch. All internal nodes are fully branched. All leaves have no children. Click. Complete binary tree. All levels are filled from left to right. The only exception is the last level, which may be partially filled, but it must fill from the left with no gaps. This structure is exactly what makes heap storage in a flat array work correctly, as we'll see in the heap slide. Click. Perfect binary tree. Every internal node has exactly 2 children, and all leaves are at the same level. It's the most ideal shape. The formula is precise. A perfect binary tree of height h contains exactly 2 h plus 1 nodes. Height 2 gives 7 nodes. Height 3 gives 15. Perfect trees double in size with each new level. Ext. Let's write the actual Python. Every tree is built from nodes. Click. Tree node is minimal and clean. 3 attributes. Val for the data. Left for the left child, right for the right child. Both children default to none. A node with no children set is a leaf by definition. The __repr__ makes debugging clean. Click. Binary tree is a thin container. It just holds a reference to the root node. Is _empty. Checks whether there's a root. You could work with bare tree node references throughout, but having a container makes the intent explicit when you're building reusable classes. Click. Building a tree manually. We construct nodes one by one and wire them together. The comments show the shape in line. Root is 1. Left subtree under 2 has children 4 and 5. Right child 3 has only a right child, 6. Reading the construction top to bottom, you can trace the shape mentally. Click. The 2 utility functions, height and size, both follow the same recursive pattern. Base case, none returns a sentinel value. Recursive case. Process both subtrees and combine. Height returns -1 for empty to correctly handle the edge case of a single leaf having height 0. Size simply counts 1 for this node, plus all nodes in the left subtree, plus all nodes in the right subtree. Both are ON, visiting every node exactly once. Traversal means visiting every node in the tree exactly once. There are 4 standard traversal orders, and the one you choose depends entirely on what you're trying to accomplish. Look at the table. Preorder visits root first, then recurses left, then right. Result: 1, 2, 4, 5, 3, 6, 7. The root appears first in the output, hence pre. In order recurses left first, visits root in the middle, then recurses right. Result: 4, 2, 5, 1, 6, 3, 7. Root in the middle, in. Post order recurses both subtrees first, visits root last. Result: 4, 5, 2, 6, 7, 3, 1. Root last, post. Level order visits nodes, level by level using BFS. Result: 1, 2, 3, 4, 5, 6, 7. Click the memory trick. The prefix tells you where the root goes relative to the children. Pre, root first. In, root in the middle. Post, root last. Pre-order is natural for copying or serializing a tree. In order on a BST gives sorted output, the most important traversal for search trees. Post order is natural for deleting a tree or evaluating expression trees. Level order is natural for finding shortest paths, printing by level, or any breadth first problem. 3 traversals in code, and then the iterative version. Click preorder. Append the current node's value immediately on entering, then recurse left, then recurse right. The root is always first in the output list. The recursive structure mirrors the definition exactly. There's almost no translation from definition to code. Click in order. Recurse left all the way down first. Append the current value when you return from the left branch, then recurse right. The current node's value always lands between its left and right subtrees. On a BST, which we'll see shortly, this produces a sorted sequence. Click post order. Recurse both children before appending the current value. The current node's value is always last. This is the correct order for computing bottom-up results, like evaluating an expression tree, or freeing memory while ensuring children are freed before parents. The output from the demo tree, pre-order, 1, 2, 4, 5, 3, 6, 7. In order, 4, 2, 5, 1, 6, 3, 7. Post order, 4, 5, 2, 6, 7, 3, 1. Click iterative pre-order. Avoids the call stack entirely, essential for very deep trees that would hit Python's recursion limit. We use an explicit stack. Start with the root, pop a node, append its value, push right child first, then left child. Because a stack is LIFO, left was pushed last, so it gets popped first, maintaining left before right order. Clean and efficient. Level order traversal is the tree version of breadth first search, and the variant that returns nodes grouped by level is extremely common in interview problems. Click the implementation uses a dequay for efficiency. Pop left is O1 on a dequay versus ON on a list. The key technique is capturing len, Q, before the inner loop. That count tells you exactly how many nodes are on the current level right now. We process exactly that many nodes, appending their children for the next iteration. This neatly produces one sublist per level in the output. The result for our example tree: 1, 2, 3, 4, 5, 6, 7. 3 levels, clearly delimited. Click zigzag level order is a common twist. Same structure, just reverse alternate levels before appending them. A left underscore to underscore right flag toggles each iteration. Level 0, left to right. Level 1, right to left. And so on. The code change is minimal, one line of conditional reversing. Click the diagram on the right, traces the Q state step by step. Start with 1. Population 1, in Q2 and 3. Population 2, in Q4 and 5. Population 3, on Q6 and 7. Population 4, 5, 6, 7. No children. Q empty. Traversal complete. Each pass through the outer, while loop processes exactly one level. Ext. The BST is the most algorithmically important tree variant. It adds one constraint on top of binary tree structure, and that constraint enables efficient search. Click the BST property. For every node n, all values in the left subtree are strictly less than n.val, and all values in the right subtree are strictly greater. This ordering must hold for every subtree, not just the root. It's a global invariant. Click on a balanced BST. This property lets you have the search space at every node, just like binary search on a sorted array. That gives O log n for search, insert, and delete. We'll see what balanced means precisely in a later slide. Click the callout is extremely useful in practice. In-order traversal of any BST yields its elements in sorted ascending order. The BST diagram confirms it. Reading the nodes in order left to right through the shape gives 1 3 4 6 7 8 1 0 1 3 1 4. This property is what makes BSTs the natural structure for maintaining a sorted dynamic set. Click Trace the shape of the diagram. Root is 8. Left subtree has all values less than 8 to 3, 1, 6, 4, 7. Right subtree has all values greater than 8, 10, 14, 13. Null children are shown explicitly to reinforce that the shape is a binary tree. Some nodes have one child, some have two. Next, insert and search follow directly from the BST property. They're both OH, where H is the tree's height. Click Insert uses a recursive _ insert helper. Base case, we've reached a null slot. Create a new leaf here and return it. Recursive case, if the new value is less than the current node's value, recurse into the left subtree. If greater, recurse into the right subtree. Equal values are ignored. This BST stores no duplicates. The parent always receives the returned reference, which links the new node into the tree. A clean functional style that avoids parent tracking. Click Search is almost identical in structure. If we hit none, the value isn't in the tree. Return none. If the current node matches, return it. Otherwise, recurse left if the value is smaller, right if larger. At each step we eliminate half the remaining tree. OH time. Click the demo inserts, 8, 3, 10, 1, 6, 14, 4, 7, 13. The exact BST shown on the previous slide. Search 6 returns the node. Search 99 returns none. In order confirms 1, 3, 4, 6, 7, 8, 10, 13, 14. Sorted. Click the insert diagram shows adding 5 to that BST. Starting at root 8 to 5 is less, go left to 3. 5 is greater, go right to 6. 5 is less, go left to 4. 4 has no right child, insert here. The search trace shows search 4. 4 less than 8 right pointing arrow go left to 3. 4 greater than 3 right pointing arrow go right to 6. 4 less than 6 right pointing arrow go left, found 4. Next. Deletion is the trickiest BST operation because it has 3 structurally different cases. Click Case 1. Leaf node. The node to delete has no children. Simply remove it. Return none to the parent. Case 2. 1 child. The node has exactly 1 child. Replace the node with that child. Return the child reference to the parent. Case 3. 2 children. This is the interesting case. We can't just remove the node because it holds 2 subtrees together. The standard solution. Find the in-order successor, the smallest value in the right subtree. Copy that value into the current node, then delete the successor from the right subtree. The successor is always either a leaf or has only a right child, so its own deletion falls into case 1 or 2. Click the _delete helper handles all 3 cases. Recurse left or right to find the target node. On a match with 2 children, find the minimum of the right subtree using _min_node, copy its value, then delete that minimum from the right subtree recursively. Return the possibly modified node, back up the chain. _min_node walks left as far as possible. The leftmost node holds the minimum value in any BST subtree. Click the diagram shows deleting node 3 from the BST. Node 3 has 2 children, 1 and 6. Its in-order successor is 4, the smallest value in the right subtree rooted at 6. We copy 4 into where 3 was, then delete the original 4 leaf from the right subtree. The BST property is preserved throughout. Next. Here's the critical nuance about BST performance. O log n for BST operations only holds when the tree is balanced, when the height is proportional to log of n. The left diagram shows a balanced tree with 7 nodes and height 2. Click the right diagram shows what happens when you insert already sorted data, 1, 2, 3, 4, 5 in order. Each new value is always larger than all existing values, so it always goes to the right. The tree degenerates into a right-skewed linked list. Height equals n-1. Search, insert, and delete all become on. You've lost every advantage the BST was supposed to give you. This isn't a pathological edge case. It happens in practice whenever input arrives in sorted or nearly sorted order. And it's why self-balancing trees were invented. AVL trees and red-black trees guarantee O log n by automatically restructuring themselves after every insert or delete. Python's sortedcontainers.sortedList uses a different but equally effective approach. We'll look at AVL trees next. The AVL tree, invented by Adelson, Velsky, and Landis in 1962, was the first self-balancing BST. Its invariant is elegant and precise. Click every node stores a balance factor, the height of its left subtree minus the height of its right subtree. The AVL invariant. That balance factor must always be -1, 0, or +1. The moment any node's balance factor reaches +2 or -2 after an insert or delete, a rotation is performed to restore the invariant. Click the code implements the 4 helper functions. Underscore H returns the stored height safely, handling none. Underscore BF computes the balance factor. Underscore UPD recalculates a node's height after its children change. Underscore rot underscore right and underscore rot underscore left perform single rotations. The rotation rewires 3 references and updates heights in the correct order, children before parents. Click underscore balance is called on every node on the path back to the root after an insert. It checks the balance factor and dispatches the correct rotation. Left heavy by 2. Check if it's a left-left case or a left-right case. Left-right requires a left rotation on the child, before the right rotation on the parent, the double rotation. Symmetric logic for right-heavy nodes. Click the diagram shows the simplest LL case. A chain C left pointing arrow B left pointing arrow A has balance factor +2 at C. A single right rotation makes B the new root with A and C as children, perfectly balanced. The rotation table enumerates all 4 cases, LL, RR, LRRL, and which rotations fix each one. A binary heap is a complete binary tree stored as a flat array, and that combination of properties gives it remarkable efficiency. Click the heap property defines the ordering. In a minute heap, every parent is less than or equal to both its children. The minimum element is always at the root. In a max heap, every parent is greater than or equal to its children. The maximum is at the root. Click the array representation is the clever part. Because a heap is always a complete binary tree, there are no gaps in the level order layout. This means we can store the entire tree in a compact array with no pointers at all. The parent-child relationships are encoded in the indices themselves. For zero-indexed arrays, the parent of index I is at I1/2. The left child of I is at 2I plus 1. The right child is at 2I plus 2. Click, the diagram visualizes 1, 3, 5, 7, 9, 8, 6 as both its array form and its tree form simultaneously. Root is index 0 with value 1. Its left child is index 1 with value 3. Its right child is index 2 with value 5. Check the relationships manually. Left 0 equals 1 gives us the value at index 1, which is 3. Click the callout. Python's heapq module implements a minute heap directly over a plain Python list. You don't need to import a special class. Any list can be a heap once you call heapify on it or use heappush to populate it. The smallest element is always at index 0. The complete heapq API in one slide. Click push and pop. Heappush inserts a value and sifts it up to its correct position, O log n. Heapop removes and returns the minimum, sifts the replacement element down, O log n. After pushing 5, 1, 9, 3, the heap list is 1, 3, 9, 5. Heap order, not sorted order. But H0 is always the minimum, and pops always return elements in ascending order. Click heapify, converts an arbitrary list into a valid heap in place, ON. This sounds surprising, given that individually pushing n elements takes ON log n, but the bottom-up heapify algorithm is provably ON. Use heapify when you have a pre-existing list. Use repeated heappush when elements arrive one at a time. Heappushpop and heapreplace are atomic push-pop combinations, more efficient than calling them separately. Use these in hot paths, like maintaining a fixed-size top K window. Click max heap via negation. Python's heapq is min heap only. The standard workaround: negate all values on push, negate again on pop. Heappush, max_h, -v. Heapop, max_h gives the most negative value. Negate it to get the largest original value. Click NL largest and N smallest are convenience functions for one-shot top K queries. They run in ON log K, efficient when K is much smaller than N. Heap sort is the clean demonstration that a heap is a sorting algorithm in disguise. Heapify the array in ON, then pop all elements. Each pop is O log n, n times total. ON log n, guaranteed, in place, stable, well actually not stable, but ON log n with O1, extra space. Ext. A trie, short for retrieval tree, is a specialized tree for storing strings by sharing common prefixes. If you've ever used autocomplete, you've benefited from a trie. Click each trie node holds a dictionary of children, keyed by character, and an is_end flag that marks whether a complete word ends at this node. The root node represents the empty string. Click insert walks the trie one character at a time. If the current character doesn't have a child yet, create one. Advance to that child. After processing all characters, mark is_end equals true. OM, where M is the word length. Search is almost identical. Walk the path. But we return false the moment any character is missing. Return true only if we reach the end of the word and is_end is true. That last check is critical. CA is not a word in the trie, even if car is. Click starts underscore with is like search but returns true. As soon as we've successfully consumed the entire prefix, we don't care whether his underscore end is set. This is what makes autocomplete work. Check if any path starts with the user's current input. Delete uses a recursive cleanup. After removing the target words is underscore end flag, it checks whether the current node has become structurally unnecessary. No remaining children, no other word ending there. If so, it signals the parent to remove the reference. Click the diagram shows the try after inserting car, cat, can, and dog. The root branches to C and D. The C branch to A, which branches to R, T, and N, sharing the prefix CA. The star marker shows is underscore end equals true. No character is stored twice for the shared prefix. That's the whole point. Next. A segment tree answers range queries, sum, minimum, or maximum over an interval, and handles point updates, both in O log n. It's the structure of choice whenever you have a range query plus update combination that would be ON with a naive array. Click the tree is built recursively over the input array. Each leaf represents a single element. Each internal node represents the aggregate of its subtree's range. For a sum segment tree, every internal node stores the sum of all elements in its range. Building takes ON. We visit each node once. Click query takes a range and navigates the tree. 3 cases at each node. If the query range is completely outside the node's range, return the identity value, 0 for sum. If the query range completely covers the node's range, return the stored value directly. Otherwise, split at the midpoint and combine results from both children. This selective traversal ensures we visit O log n nodes per query. Click update walks down to the target leaf, updates it, then recalculates all ancestor values as we unwind. Also O log n. The demo, array, 1, 3, 5, 7, 9, 11. Query sum, 1, 3, equals 3 plus 5 plus 7 equals 15. Update index 2 to 10. Query sum, 1, 3, again equals 3 plus 10, plus 7 equals 20. Click the tree diagram maps every internal node to its range and its current sum. The root covers 0 to 5 with sum 36. Left child covers 0 to 2 with sum 9. Right child covers 3 to 5 with sum 27. The leaves hold the individual values. A single update percolates changes upward through exactly the ancestors of the modified leaf. 4 essential tree algorithms that appear constantly in interviews and competitive programming. Click are 2 trees identical? Structural and value equivalence. Recurse simultaneously through both trees. Base case. If both are none, true. If exactly one is none, false. Otherwise, check that values match and recursively confirm left subtrees match and right subtrees match. Short circuits on the first mismatch. ON. Click invert, mirror a tree. Swap left and right children at every node. The recursive one-liner does it elegantly. Swap the children, passing each side recursively before assigning. Post order by nature, children are inverted before the swap. ON. Click is the tree balanced? Not just checking the root. A tree is balanced only if every subtree satisfies the balance condition. The inner check function returns the height if balanced, or -1 as a sentinel if any subtree is found unbalanced. We propagate the -1 upward, short-circuiting. A single pass. ON. The outer function just checks whether the result is non-negative. Click lowest common ancestor in a BST. The LCA of 2 nodes is the deepest node that is an ancestor of both. In a BST, the answer uses the BST property directly. If both target values are less than the current node, the LCA must be in the left subtree. If both are greater, it's in the right subtree. The moment they diverge, one is less and one is greater, or one equals the current node, this is the LCA. OH no recursion needed. Diameter, the longest path between any 2 nodes in the tree. At every node, the best path through it is left underscore height plus right underscore height. Track the global maximum using a closure variable. ON. Next. 4 more. Path problems and serialization. Click has path sum. Does any root to leaf path sum to the target? Recurse. Subtracting the current node's value from the target. Add a leaf. Check if the remaining target equals 0. ON. Potentially visiting all paths. Click all root to leaf paths. DFS with backtracking. Append the current node on entry. If it's a leaf, record a snapshot of the path. Otherwise, recurse to children. On return, pop the current node. This is the backtrack. The list, path snapshot is critical. You must copy the path at the leaf, not store a reference to the mutable list. Click serialize and deserialize. Serialization is pre-order traversal with hash as a null marker. Every node becomes its value as a string. Every none becomes hash. Join with commas. The output 1, 2, 4, hash number 5, hash number 3, number 6, hash hash. encodes the full tree structure unambiguously. Deserialization consumes the tokens one by one, using a stateful iterator. Hash tokens return none. Any other token builds a new node and recursively builds its left and right children from the iterator stream. Preorder structure means left subtree tokens always precede right subtree tokens. The recursive calls consume them in the right order automatically. Click running in order on the deserialized tree produces the same sorted sequence as the original, confirming correctness of the round trip. An n-ary tree node can have any number of children, not just two. This generalization handles real-world hierarchies like file systems, XML documents, and org charts, where branching factor varies. Click-nary node stores a list of children instead of left and right. The default is an empty list. A node with no children is a leaf. The rest of the traversal logic adapts naturally. Click preorder on an n-ary tree, append the root value, then recursively traverse each child in order. Postorder, recursively traverse each child first, then append the root. Level order, same dequay-based BFS, but instead of enqueuing left and right, we queue.extend, node.children, all children in one call. Click the diagram shows the example try. Root 1, children 3, 2, 4, where node 3 itself has children 5 and 6. Preorder gives 1, 3, 5, 6, 2, 4. Level order gives 3, 2, 4, 5, 6. Click left child right sibling encoding is the classic technique for converting any n-ary tree into a binary tree without losing information. Each node's left pointer becomes its first child. Each node's right pointer becomes its next sibling. The bottom diagram shows the encoding. Node 3 is the left child of 1. Node 2 is the right sibling of 3. Node 4 is the right sibling of 2. Full n-ary structure, stored as a binary tree. Ext. Full complexity reference. All tree variants in one place. Click binary tree. All traversals are ON. You visit every node. Space is OH for the recursion stack, proportional to tree height. In the worst case, a degenerate tree has ON height and ON stack space. In a balanced tree, it's O log n. Level order uses OW space, where W is the maximum width of the tree, which can be ON for a very bushy tree. Click BST. 3 columns. Average balanced case is O log n for all operations. Worst case, degenerate tree, is ON. Always. This is the key takeaway. A plain BST gives you probabilistic O log n, with random data, but no guarantee. AVL and red-black trees guarantee O log n, for all operations unconditionally by maintaining balance. That guarantee is why production databases and language standard libraries use balanced BST variants rather than plain BSTs. Click heap. Push and pop are O log n. Heapify is ON, the non-obvious but provable result. Peaking the minimum is O1, it's always at index 0. NL argest k is ON log k. Try. All operations are OM, where M is the key length, independent of how many words are stored. Space is ON times M, number of words times average length. Segment tree. Build once in ON. Each query and update is O log n. Decision guide. Which tree structure to reach for given a specific problem. Click you need fast sorted operations. Insert, delete, and search with O log n guarantees. Use a balanced BST. In Python, that means sorted containers.sortedList, or a custom AVL tree. You need the minimum or maximum of a dynamic set efficiently. Use a binary heap via heap queue. You need prefix matching, autocomplete, or string searching by prefix. Use a try. You have an array that needs range sum or range minimum queries with point updates. Use a segment tree. You're modeling a hierarchy with arbitrary branching, file system, DOM, org chart. Use an n-ary tree. If you're doing BFS or DFS on a structure that has cycles, or you need to model bidirectional relationships, that's no longer a tree. Use a graph. A tree is just a special case of a directed acyclic graph. The diagram encodes this decision flow directly. Start from your requirement. Follow the edge that matches. Arrive at the right data structure. Let's close out with the mistakes that trip people up and the patterns that prevent them. Click Pitfall 1. Recursive traversal on huge trees. Python's default recursion limit is around 1,000 frames. A tree with depth greater than that, a degenerate BST with 10,000 nodes inserted in sorted order, for example, will raise recursion error. Switch to iterative traversal for production code. Pitfall 2. Using a sorted list as a BST substitute. Sorting a list after each insert is ON log n per operation. A balanced BST gives O log n. Not the same thing. Pitfall 3. Inserting sorted data into a plain BST. We showed this. It degenerates to a linked list. Shuffle your data, or just use a self-balancing structure. Pitfall 4. Forgetting none checks. Node.val raises attribute error, if node is none. Always guard with if node, or if node is not none. Click Best Practice 1. Iterative in order. The code uses an explicit stack and a cur pointer. It's the standard pattern. Walk left as far as possible, pushing onto the stack. Pop, record the value, move to the right child. Works for arbitrarily deep trees with no recursion overhead. Best Practice 2. Sorted containers.sortedList, for a balanced BST without implementing your own. It's a drop-in sorted container, backed by a B-tree variant. O-log-n, for add and discard, pure Python. No C extensions required. Best Practice 3. Always guard if node before accessing .val in recursive and iterative code alike. Ext. Everything in one view. Click the taxonomy diagram maps the full family. Tree splits into binary tree and n-ary tree. Binary tree specializes into BST and heap. BST further specializes into AVL and red-black for self-balancing guarantees. N-ary tree gives rise to the trie and the segment tree as domain-specific specializations. Click Traversal Order Recap. Pre-order, root, left, right. In order, left, root, right, gives sorted output on a BST. Post-order, left, right, root, bottom-up processing. Level order BFS, level by level. Click the Quick API block is your reference code for all 4 structures. BST insert, search, delete, and in-order traversal. Heap push, pop, heapify, peek. Try insert, search, and prefix check. All 4 traversal functions. Click Final Complexity Summary. Balanced BST gives O log n for all operations. Heap gives O log n, push and pop, O1, peek min. Try gives OM for all string operations, proportional to key length, not number of keys. Segment tree gives O log n for range queries and point updates. That's trees. Knowing when to reach for each variant, BST for ordered sets, heap for priority queues, try for strings, segment tree for range queries, is the skill this video was built to give you. And that's the complete guide to trees. We went from root to leaf. Literally. Tree terminology, binary tree types, all 4 traversals, BST insert/search/delete, balanced versus degenerate, AVL rotations, binary heaps and heap queue, tries with prefix search, segment trees for range queries, 8 common algorithms, n-ary trees, and the full complexity breakdown. If this was useful, hit like and subscribe. Drop questions in the comments. I read all of them. See you in the next one.